So here we're going to go to the mechanism for the Pinacol rearrangement. And as always, the first thing you want to do is look over the arrow and see what the reagents are. We see acid here, it's acid catalyzed. So I'm going to put a circle over here on the right-hand side. And that circle, I'm going to put a plus sign, and that's going to help keep track of my math and make sure that I don't put any minus signs anywhere in the mechanism. Okay? Okay, so when I start with the Pinacol, I have a symmetrical glycol. And it doesn't really matter which oxygen I protonate to get this reaction going. And it's a 50-50 shot because these are the same oxygen, the same nucleophilicity. It's a symmetrical molecule. So we can protonate either oxygen. So what I'm going to do is I'll just randomly pick one. And I will start off the mechanism by protonating the oxygen on the left. So you'll see here I'm going to protonate the oxygen left. I'll use the lone pair of electrons on the oxygen as the nucleophile, which goes up to the electrophile. That will pick up the proton, and that is going to make an oxonium ion. And so we know that the what's going to happen there, because we've seen this literally dozens and dozens of times, we're going to make the H2O a better lead group, because the OH is a crappy lead group. When you protonate it to make H2O, it will fall off as neutral water, and that is going to be a much better leading group. So that's what we'll do here. We will have H2O fall away, and so we'll lose water, and we'll lose one equivalent of water to make a nice tertiary carbocation, which is a pretty good, strong carbocation, but not the best. I mean, what is better than a tertiary carbocation? Not many things, but one thing that is better is going to be a resonance-stabilized tertiary carbocation. So here we can say I've got two methyl groups on the right-hand carbon, which I can do a 1,2 something something shift on. And so if I do a 1,2 something something shift and have the methyl move over one carbon, what that'll do is it'll make a T-butyl group on the left, and then what that will leave behind on the right is a tri-substituted tertiary carbocation that's going to be resonance stabilized, because you have the lone pair of electrons on the oxygen that can dump down onto the carbocation in resonance and make it a resonance stabilized carbocation. Therefore, when you do the 1,2 something something shift, and you never want to do those unless you're going to end up someplace more stable than you started, but here that's exactly what happens. We see this carbocation that's resonance stabilized, so I can take the lone pair of electrons on the oxygen, and so I will take the lone pair of electrons on the oxygen. I will have them resonate down towards the plus charge. That's what electrons do. That will give me a double bond, making a carbonyl, and that turns the hydrogen, which has a pKa of 16-17 for an alcohol hydrogen, but that's going to turn it into an oxonium ion hydrogen, which has a pKa of -2 or -3. Very, very acidic. Therefore, I can use a general base, so I'll use the general base notation of B-, and I'll use a general base to be the base that will pull off the proton, give the lone pair of electrons back to the oxygen, and leave you with the stable product, which is going to be the ketone that we see up in the reaction on the top of the screen as the product we're going for. So this is called the Pinacol rearrangement of Pinacol to make pinacolone. That's the old-fashioned name for this compound. Pinacolone is a ketone with an O-N-E suffix. If you want to give it a more of a UPAC name or a standard name, we would say that actually what this is it is a butanone. It's a 4-carbon ketone. So we can number our carbons 1, 2, 3, 4, and so we see here that actually what we have is a 2 methyls on carbon number 3, so we'll call it a 3,3 dimethyl. Then the ketone is on carbon number 2, so that is going to be a 2-butanone. So the full name for this would be a 3,3 dimethyl 2-butanone with an O-N-E suffix, or butane 2-one with an O-N-E suffix for the name there. So there are many kinds of Pinacol rearrangements. What you need to start with is a glycol, a 1,2 diol. If you have a 1,2 diol, which you can create by taking an alkene and reacting with dilute CmNO4 or with osmium tetroxide. But if you have a alkene, you turn into a diol. It's a vicinal diol. Then you can do a Pinacol rearrangement on that molecule. So the one I'm showing here on the screen for the actual one where that gets your name, the Pinacol rearrangement, that's a symmetrical molecule. But look at the ones on the screen here. This is an asymmetrical diol. That glycol has different groups on the left and on the right that are going to do the 1,2 something something shift. So therefore, how many products can you get? Well, I'm showing you 2 products here, and both of these products are coming from starting off the mechanism the same way, and that is going to be protonating the oxygen on the left between the glycol. So let me show you this reaction here to get to these 2 products you're seeing on the right. And remember, they both arise from protonating the alcohol on the left. You're going to get the oxonium ion, it falls off as water, and then you're going to generate this cation. It'll be a benzoic cation once the water falls off. And then from here, we have 2 possible rearrangements that we can do. We can say, well, okay, so I got a cation, I want to rearrange. I can do a 1,2 hydride shift. That'll give me a rearrangement. But then I could also do a 1,2 methyl shift, and that's a different rearrangement. And they'll both result in different ions. So here on green, I'll do the 1,2 something something shift where the hydride does the shift. Okay, so then we'll take the molecule at the top of the screen and call it the first molecule A. We'll call it product A. We'll call it the green one. So if we follow the green arrows for that one, we'll get to there. The other one we'll call blue, and we'll call that one molecule B or product B. That'll be the blue arrows we're going to look at in the mechanism. So for A, if I take the hydride and I do the 1,2 something something shift, that will leave behind a cation over by the oxygen. That's a resonance stabilized cation. And then you follow through the exact same mechanism where you're going to take the cation, you're going to have it resonate the electrons down to the oxygen, you're going to remove the proton from the oxygen, and then you're going to make product A as the result of that. I'm not going to just draw this all out for you because it's exactly the same as on the previous slide, so you should practice. And that's a good thing to fill in here on this mechanism, fill in all the blanks by practicing how you do this. So that's from the 1,2 something something shift where you have the hydrogen doing the shifting. Now that's product A. What about product B? So we'll do blue arrows for product B. So we're going to have the cation, then we're going to do the 1,2 methyl shift. That'll leave behind a cation on the carbon, which will have the electrons resonate down from the oxygen, which makes the oxytonium ion, which then uses the general base to pull off the proton. That makes product B. And so you look at these, do you think products A and B are going to be formed in equal yields? And the answer is, well, probably not. Why is that? Well, because when we go through the 1,2 something something shift, they both start at the same cation, the benzylic cation after the rate determining step there. But then product A is going to rearrange to a cation for the next intermediate that's going to have a nice tri-substituted resonance stabilized cation because you're going to do the 1,2 hydride shift and leave the methyl behind. If you're going to do product B, you're going to do a 1,2 methyl shift, leaving the hydrogen behind, and that's going to be a less substituted carbocation, which is less stable. And that's the one that leads to the aldehyde. So the one that leads to the ketone, product A, is going to go through a transition state in a mechanism, and an intermediate that is more stable because it's got the better carbocation. So they're not going to be formed in the same yield. As a matter of fact, these will not be the only two products. There's another two products. What if instead, in the first step, instead of protonating the oxygen on the left, I protonate the oxygen on the right? Well, I'd make two more compounds. So if I protonate the oxygen on the right and drop off the OH as water on the right-hand carbon, and I make the carbocation there, then I've got two possibilities for the shift. I've got the 1,2 something something shift where the hydride goes from the left to the right in the structure, or I can do a 1,2 something something shift where the phenyl does a shift from the left to the right in the structure. That's going to give me two more different carbocations. And those carbocations are going to lead to two more different products. And I can show you what those products are going to be. So if we do the 1,2 hydride shift here, that'll leave behind a benzylic carbocation, which then when the oxygen collapses down, that's going to make a ketone. So they'll do two more products, we'll call them C and D. So here's going to be the product C. And so we're going to get a phenyl ketone because we did the 1,2 hydride shift. So we'll call this product C. And then the other product you can get is where instead of doing the 1,2 hydride shift, you do the 1,2 phenyl shift. And we do the 1,2 phenyl shift, leaving the hydrogen behind on the carbon. Now when that collapses down with the resonance form and then loses the proton, you make another aldehyde. Okay. So these two molecules we'll call molecules C and D. And so if you compare these, there's this four different molecules here, four different products, and they go through different pathways in the mechanism. And it gets kind of tricky figuring out, well, which one's the major product here? You can look at the intermediate carbocations, but one of these are not, we haven't talked about this yet this year, but here's another little curveball that gets into the mix here. It makes a difference when you're talking about the rearrangements, which one of the groups is a methyl, the same, does it have the same ability to do the migration, the 1,2 something something shift as a ethyl? And how about as an isopropyl? Are they all the same? How about a phenyl? Are they all the same? The answer is no. If you think about it, when you do a 1,2 something something shift, you're shifting to go towards a carbocation, which means the thing that shifts is a nucleophile. It's taking its electrons with it when it makes the bond, breaks the bond, and then makes the bond. So when the methyl does a methyl shift, the methyl is a nucleophile. When the hydride does a shift, it's a nucleophile. When the phenyl does a shift, it's a nucleophile. So therefore, we call it in these types of rearrangements, we call it migratory aptitude, meaning not all groups that are doing some shifts are equally adept at doing the shift. The more nucleophilic ones are going to be the ones that will do the shift faster and easier. And we didn't have to worry about that on the previous slide because we were, it was a symmetrical molecule where it was always going to be a methyl shift doing the 1,2 something something shift. So it didn't really make any difference. But on the new slide where we're looking at different substituents, it's a hydride in one case, it's a methyl in another case, and it's a phenyl in the other case. So that's three different migratory aptitudes. So you have to worry about that when you're doing it on asymmetrical glycols. And and so how do you predict which ones are have better migratory aptitude? Well, it's the ones that are more electron rich. And you can sort of begin to predict this and think about this because we've already talked about this kind of in class. Where let's, for instance, talk about a benzene ring, and we want to do electrophilic aromatic substitution on a benzene ring. And that benzene ring is going to be substituted. And we're going to substitute it with a methyl in one case, and we can substitute with an isopropyl in another case. And so then we're going to say, now let's do electrophilic aromatic, let's say, bromination on these two compounds and have a head-to-head comparison of them and see which ones would work easier. So we'll take the one benzene. I said it has a isopropyl, and I'll do that one on the bottom. And on the top here, I'm drawing the top right side of the screen. It's going to be a methyl benzene. So we're going to look at the methyl as a sigma donor and orthopower director. On the top one, you have a methyl group, and then the bottom one, you have an isopropyl group. And the isopropyl group is more electron rich. It has bigger clouds of electrons on the isopropyl. And what that means is neither one of them are donating by resonance, but by induction, by this sort of like electron cloud smushy type thing. They're both orthopower directors, but the isopropyl is going to be a more electron rich orthopower director. Therefore, in the migratory aptitude of a Pinacol rearrangement, the isopropyl is considered a better migrating group than the methyl because it's more electron rich. It's more nucleophilic, because that's the way we sort of think about nucleophilicity or migratory aptitude when we do Pinacol type rearrangements. So the way you get this on an exam would be, I wouldn't say, so here's 4 possible products in the form. Which one is going to be the one that's formed in the greatest yield? Because it gets too complicated. The way I'd present this maybe is I would say, I went in the lab, I did this reaction, this is what happened. Now you can draw the mechanism, you can think about the intermediates, you can think about the carbocations, and then you can say, well, here's the lab data, here is the actual percents. Therefore, now that I know what the actual outcome is for the experiment, I can go backtracking, I can then therefore rationalize why is the one reaction better than the other. You do that kind of answer on a problem after you have the lab data that shows you the actual numbers, not to try to predict this, because if it gets really, really messy because you got competing effects, and the competing effects here are going to be which one is the more stable carbocation to form first, and then which one has the greater migratory aptitude to form the second carbocation in the rearrangement. And that can make it very, very messy to try to predict the product here. So that's not the way we do it on an exam. So that is the mechanism for the Pinacol rearrangement.